Welcome, everyone. We're so glad you could join us for this deep dive. Today, we're tackling one of those huge fundamental questions that people have wrestled with forever. You look up at the stars or just, look around you at anything, and you can't help but wonder, what is all this really made of? What's the smallest possible thing? The ultimate building block of, everything. Stars, planets, us. What's at the very bottom?
It's such a profound question, isn't it? And that curiosity, that deep need to understand our place and the nature of reality, it stretches back thousands of years. It's truly universal. If you look back in ancient India, for example, they had this concept of the Panchmahabhuta, the five great elements.
Earth, water, fire, air, and space.
Exactly. And these weren't just, physical substances like we think of them now. They were seen as fundamental essences, the very sort of fabric of existence. And the ancient Greeks, too, they were on a similar quest. They proposed their four elements: earth, water, fire, and air. Different cultures, different times, but that same drive to figure out what the world is made of. But then, things really shifted with the scientific revolution. We started developing new tools, new ways of thinking, much more rigorous methods, and eventually this led to the discovery of the atom. For a while, everyone thought, okay, this is it, the indivisible particle, the ultimate brick.
The end of the road, so to speak.
Precisely. But science, it never really stops asking questions, does it? As our tools got better, our theories more sophisticated, we realized atoms weren't solid little balls at all. They're mostly empty space, actually, with even smaller things inside them. Protons, neutrons, electrons buzzing around. That discovery alone was mind-blowing. Suddenly, solid matter wasn't so solid, and the digging didn't stop there. Fast forward to the 1960s, and physicists using powerful new machines, particle accelerators, started smashing protons and neutrons apart. And what did they find inside? Quarks. These tiny, really elusive particles tucked away deep within.
So another layer peeled back.
Another layer. Each step showed us that what we thought was fundamental wasn't. It just kept getting smaller, more complex.
It's an amazing journey, really. Just constantly refining our picture of reality. Find smaller and smaller pieces. Incredible.
Absolutely incredible. But even after finding quarks, some physicists, the really sort of visionary ones, they started asking an even bolder question, a truly radical one. They asked, what if particles, even these fundamental quarks and electrons, what if they aren't the final answer? What if deep down at the very heart of reality, it's not about tiny points of matter at all? What if it's something else entirely? Like tiny vibrating strings of pure energy.
Strings, like on a violin or a guitar. Is that the kind of picture I should have?
And that's exactly the image. You've gone straight to the core metaphor.
Yes.
Think about it, not like the universe is some giant clockwork machine, with gears and parts. Instead, imagine it's a vast, magnificent orchestra. And in this cosmic orchestra, every fundamental particle we see, an electron, a quark, a photon-carrying light, isn't a tiny bead. It's an unimaginably small, invisible string. And each of these strings is vibrating constantly. And here's the beautiful part. Each string vibrates at its own unique frequency, its own rhythm, and that vibration is what determines what the particle is, its properties, its mass, its charge. So one particular vibration, like one note, makes an electron. A different vibration makes, say, an up quark. Another makes a down quark. Change the vibration, you change the particle.
Wow.
It's like the entire universe, everything we see and interact with, isn't built from solid bricks, but from music, a cosmic symphony that's been playing since the very beginning of time.
So, hold on. If I'm following this, the universe itself at its most basic level is essentially music, a pattern of vibrations.
Yes.
That's genuinely breathtaking. It kind of changes everything.
It really does. It's such a profound and, yes, poetic way to think about reality. It shifts us from just counting particles to listening for this underlying harmony, and that's exactly what we want to explore in this deep dive, this revolutionary idea, string theory. Well, look at how it even came about. It was almost accidental, really. We'll explore why it's grabbed the attention of so many brilliant physicists, because it offers this potential path to unifying everything, explaining mysteries from black holes to the forces inside atoms, maybe even the nature of space and time itself, and crucially, trying to bridge that gap between gravity and quantum mechanics.
The theory of everything challenge.
Exactly. So stick with us. Today, we're tuning in to the Cosmic Symphony.
Okay, I'm definitely intrigued. That premise alone is fascinating. But maybe we can back up just a tiny bit. What problems was physics actually facing that made something as wild as string theory seem, well, necessary or appealing? What were the gaps?
That's a great question. It really sets the stage. So as we touched on, for a long time, atoms were thought to be it. The fundamental thing. Simple enough. Then, early 20th century, boom, we find they're made of smaller bits. Protons, neutrons in the middle, electrons orbiting. Reality got more complicated.
Right.
Then the 1960s roll around and we discover quarks inside those protons and neutrons. So, okay, are quarks the bottom? Is that the final layer? That was a big question. But there was another, arguably even bigger problem brewing. Physics had developed two incredibly successful theories, pillars of modern science. You had Einstein's general relativity, describing gravity, how planets move, how the universe behaves on large scales, works beautifully. And then you had quantum mechanics, describing the other forces, electromagnetism, the strong and weak nuclear forces at the tiny subatomic level, also works beautifully.
They didn't work together.
Exactly, they just wouldn't mesh. When you tried to apply them both in extreme situations, like inside a black hole or right at the Big Bang, the math broke down. You got nonsense, infinities. So physics had this major disconnect. How do you unify gravity with the quantum world? That was the huge challenge, the search for a quantum theory of gravity. And also, are quarks really the end of the line? That's the context. And it was right in the middle of grappling with these issues, particularly the strong nuclear force, that something unexpected happened. Late 1960s, there was this young Italian physicist, Gabriele Veneziano. He wasn't actually looking for a theory of everything or strings or anything like that. He was focused on the strong force, trying to understand how particles like protons and neutrons interact, how they scatter off each other in experiments. He was looking at the data.
Just trying to explain the experimental results.
Right. And while digging through the math, trying to find equations that matched the data, he stumbled upon this, well, really elegant formula from old mathematics, actually. And this formula described the scattering behavior perfectly, but it looked weird. It didn't seem to describe point-like particles bouncing off each other.
What did it look like?
It looked like it was describing something that could stretch and wobble and resonate, almost like tiny vibrating strings. It had these resonance patterns you wouldn't expect from simple points. It was one of those moments in science where the math tells you something completely unexpected, something radical. And pretty quickly, other physicists, Leonard Susskind over in the US, Yukiro Nambu in Japan, working independently, looked at Veneziano's formula and had the same realization. They said, wait a minute, maybe this formula isn't just a mathematical trick. Maybe it's telling us something profound about reality. Maybe, they proposed, everything isn't made of points after all. Maybe it's made of these minuscule, one-dimensional, vibrating strings of energy, and this was potentially huge because strings having a tiny length might smooth out those nasty infinities that plagued quantum gravity calculations with point particles. That was a key motivation.
That's incredible. So the idea literally emerged from the math not quite fitting the old picture. And the beauty then, if it's strings, is that the vibration is the particle. All the particles we see are just different ways these strings can wiggle.
Precisely. That's the absolute core elegance. Think back to the guitar analogy, same string, right? But pluck it differently, fret it differently, it produces different notes, high notes, low notes, different timbres. String theory proposes the same for the universe. These fundamental strings can vibrate in countless different ways. Each distinct pattern of vibration corresponds to a different particle. So one way of vibrating might manifest as an electron, another way, a photon, another, a specific type of quark. All the particles in the standard model, potentially.
Wow.
And here's something really compelling. String theory calculations naturally, almost automatically, predict a particle with the exact properties needed for the graviton.
the hypothetical particle that carries the force of gravity.
The very same. In many other theories trying to unify physics, getting gravity to fit in the quantum picture is a huge headache. In string theory, gravity just appears. It's one of the vibrational modes of the string, like finding the bass note was already built into the instrument. So, yeah, the whole incredible zoo of particles and forces we observe could just be the music played by these unseen strings. It's a picture of dynamic harmony, not static blocks.
It's such a beautiful concept.
Yeah.
To think that everything, forces, matter, maybe even us,
Yeah.
it's all part of some grand cosmic composition. It really gives you a sense of, I don't know, deep unity.
It really does, doesn't it? That sense of underlying simplicity and connection is a huge part of its appeal. And, the theory didn't just stop there, it kept developing. Initially, in the 70s and early 80s, there were actually 5 different versions of string theory, which was a bit awkward if you're aiming for one theory of everything.
Right, 5 theories isn't quite one theory.
Exactly. But then, in the mid-1990s came what's often called the second string revolution. Physicists like Edward Witten made these breakthroughs, suggesting that these 5 theories weren't actually separate. They were like different perspectives, different limiting cases of a single, deeper, more fundamental theory. And that theory was dubbed M theory.
M theory. The M stands for?
While Witten himself has joked it could stand for magic, mystery, or membrane, depending on his mood, but it's seen as the potentially more complete framework. M theory aims to be that ultimate unified theory, but it comes with a very striking feature, something essential for its mathematical consistency. It requires more dimensions than the 3 spatial ones we experience, plus time. For the math to work out, to avoid fatal inconsistencies, M theory needs, 10 or even 11 dimensions in total, 10 space, 1 time.
Okay, 11 dimensions. My brain just struggles with that. I mean, where are they? Are we talking parallel universes again? And look, if they're just needed for the math, how do we know they're, real? Isn't that a big leap?
It's a completely fair question, and it is a huge conceptual leap. First, let's clear up the parallel universe idea. That's usually not what string theorists mean here. Think of it this way. These extra dimensions aren't vast spaces like ours existing side by side. Instead, the idea is they are compactified. They're curled up incredibly tightly at every single point in our familiar space. So tiny, far smaller than an atom, smaller even than the strings themselves, that we just don't perceive them in our macroscopic world. They're hidden dimensions.
Okay, curled up. How does that work?
The classic analogy, and it's a good one, is the garden hose. Imagine you're looking at a long garden hose from really far away, like across a field. What do you see?
Just a line, basically, 1 dimension, length.
Right. You can only move forward or backward along it. But now imagine you're an ant walking on the hose. Up close, you realize there's another dimension. Right.
You can walk around the hose,
Yeah.
the circumference.
Exactly. That little circular path is an extra dimension, but it's curled up and hidden from the distant view. String theory suggests that maybe space itself is like that everywhere. At every point, there are these tiny, curled up dimensions that the strings can vibrate in. And to your point about math versus reality, that's the heart of the debate. String theorists would argue the mathematical consistency is the evidence, or at least a strong hint. Like how Dirac predicted antimatter from his equations before it was found. The math led the way. But yes, it's a point of contention. M theory also brought in these other objects called branes, short for membranes. These can be higher dimensional surfaces or spaces that strings might be attached to, or maybe even confined within. One intriguing idea is that maybe our entire 3-dimensional universe is actually a giant 3-brane floating in a higher dimensional space, often called the bulk. And this could potentially explain things like why gravity seems so much weaker than the other forces. Maybe gravity is the only force that can sort of leak out into those extra dimensions, while electromagnetism and the nuclear forces are stuck on our brain. Now, obviously, these ideas are incredibly abstract, really hard to grasp, and that's where science communicators have been so important. People like Brian Greene, for instance, his book, The Elegant Universe, back in 1999, was huge. It brought these ideas to a massive audience in a way people could actually visualize.
I remember that book. It made a big splash.
It really did. He used fantastic analogies. Strings as cosmic guitar strings playing nature's notes. Extra dimensions like hitting folds or ripples in space like that garden hose. Reality as this vast ocean of vibration. He made the complexity feel, well, elegant. And pulling it all together, the ultimate promise, the final twist string theory offers is this potential unification, the idea that everything matters. Particles like electrons and quarks, force carriers like photons, gravity, maybe even the fabric of space and the flow of time itself, they might all just be different aspects, different tunes played by this one fundamental entity. The tiny vibrating string, one fundamental ingredient composing the entire cosmic recipe.
Wow, okay. So if you really follow that thought through, maybe the universe isn't made of particles in the way we normally think, not little dots, but it's made of vibrations, music, essentially, kind of energetic resonance. That's profoundly different and kind of beautiful.
Yes, exactly. A music, a symphony, far too small and high-pitched for us to ever hear directly, but complex and rich enough to build everything from atoms to galaxies, a universe humming with energy, vibrating with potential. It's a really powerful image of interconnectedness.
Okay, but, it does sound almost too neat, too elegant maybe. It wraps everything up so nicely. If string theory is this perfect explanation, this beautiful symphony, why isn't it just, accepted fact by now? Why isn't it in all the textbooks as the answer? There has to be a catch, right? A big challenge.
Oh, yes, the catch.
Man.
And it's a very, very big one. This is where the beautiful mathematical dream runs headfirst into the hard wall of experimental science. Many physicists, even those who admire the theory's structure, are deeply skeptical, and for good reason, because string theory, despite all its mathematical beauty and promise, it has this one major hurdle. We can't test it. Not with any technology we have now, and maybe not with anything we can realistically imagine building.
Not testable at all.
Not directly, no. Think about how we confirm other theories. Newton's gravity. We see the apple fall, we measure the planet's orbits, it's verifiable, repeatable. Einstein's relativity. It made specific, weird predictions like starlight bending near the sun. Astronomers went out during an eclipse, measured it, and boom, Einstein was right. Gravitational waves predicted a century ago, detected just recently. That's empirical proof.
Observation confirms the theory.
Exactly. String theory operates on scales that are just impossibly small. The strings themselves, if they exist, are thought to be around the Planck length. That's 10 to the minus 35 meters. A proton is already minuscule, about 10 to the minus 15 meters. So a string is, 100 billion times smaller than a proton? It's almost meaningless to picture.
Yeah, inconceivably small.
Right. And to probe something that small, you need incredible amounts of energy. Far, far more energy than even our most powerful particle collider, the Large Hadron Collider at CERN, can produce. Orders and orders of magnitude more. So there's no microscope, no collider that can see these strings directly. Not now, maybe not ever. And that lack of direct experimental evidence is the theory's biggest weakness. It's Achilles' heel.
So critics would say it's basically a theory without evidence. Just really fancy, really complicated mathematics that happens to look nice, but isn't necessarily connected to physical reality. Is that the argument?
That's precisely the heart of the criticism. You have figures like Richard Feynman, a Nobel laureate, a giant of 20th century physics, who was famously very wary of theories you couldn't test. His attitude was basically, if you can't make a prediction that experiment can check, it's not science. It might be philosophy, it might be mathematics, but it's not physics in the traditional sense. Einstein himself, for all his theoretical brilliance, always insisted that nature gets the final vote. Experiment is the ultimate judge. String theory hasn't yet faced that crucial judgment.
So it can't make unique predictions we can test right now.
That's the main issue. It hasn't produced a smoking gun prediction, something only string theory predicts, that we could then go out and look for. Now, researchers are trying. They're looking for subtle things. Maybe tiny deviations in gravity at very short distances, or specific patterns in the cosmic microwave background radiation left over from the Big Bang. Maybe signatures related to dark matter or dark energy. But so far, nothing definitive has emerged that couldn't also be explained by other ideas. So string theory occupies this kind of limbo state. It sits somewhere between physics and mathematics, maybe even philosophy. It's mathematically stunning, incredibly imaginative, potentially unifying, but it's poor in experimental proof. And there's another layer of difficulty too, something called the string theory landscape. The theory doesn't seem to predict just one possible universe, like ours. It seems to allow for a truly staggering number of possible universes, maybe 10 to the power of 500, or even more, each with potentially different fundamental constants and laws of physics.
10 to the 500, that's an astronomical number.
It's unimaginably vast, and this landscape makes it really hard for the theory to predict why our universe has the specific properties it does. If almost anything is possible within the theory, how does it explain the specific reality we observe? Critics argue this makes the theory lose its predictive power. It suggests we might just be living in one random universe out of a near-infinite multiverse.
That landscape problem sounds like a really serious philosophical challenge too. So if it's untestable right now and has this landscape issue, what keeps physicists working on it? Is it purely the mathematical beauty? Especially when there are other ideas out there trying to tackle quantum gravity, like loop quantum gravity?
That's the crux of the ongoing debate. It's fascinating. On one side, you have physicists who are deeply compelled by the theory's internal consistency and, yes, its profound elegance. They argue that this mathematical beauty, the way it seems to naturally unify forces, including gravity, the way it hints at deep symmetries like supersymmetry, is itself a powerful guide. They feel it's just too compelling, too coherent, not to be on the right track somehow. They might point to historical examples where beautiful math predicted reality before we could test it, like antimatter or the Higgs boson. They believe the experiments will eventually catch up.
Beauty is a signpost to truth.
Kind of. But then on the other side, you have physicists who are equally insistent on the traditional scientific method. They say, look, elegance is nice, but it's not enough. Without experimental data, without testable predictions, it remains speculation. A beautiful hypothesis, maybe, but not proven science. They emphasize that science must be grounded in observation. Yeah. And they'd argue the landscape problem actually undermines the claim of elegance because it doesn't explain our specific universe. And yes, they might point to alternative approaches like loop quantum gravity, which starts from different assumptions about quantizing space and time itself, even though it also lacks direct experimental proof currently. So it really brings up this deep philosophical question: what is the role of mathematical beauty in science? Does truth always need immediate, tangible proof? Or can theoretical elegance sometimes be its own form of evidence, pointing the way forward, just waiting for our technology to develop? It challenges how we define scientific progress, especially when we're probing realms so far beyond our current experimental reach.
That's incredibly fascinating. If I think about the whole process of science differently. So maybe string theory isn't the answer in the way we normally think of a proven theory. Maybe it's more like a complex piece of music the universe composed, and we're still just trying to figure out how to read the score, how to understand all its nuances. Okay, so let's cut to the chase then. After this whole journey, exploring the tiny strings, the extra dimensions, the challenges, do we actually know if string theory is true? Is this the right description of reality?
The honest, straightforward answer has to be no. We simply don't know. String theory is still very much a theory in progress, a framework, a collection of ideas. It's unproven. It could one day turn out to be spectacularly right. Maybe some clever experiment or an astronomical observation will provide that crucial piece of evidence. That would be revolutionary. Or, equally possible, it could eventually be superseded. Science history is full of elegant ideas that turned out to be wrong or incomplete. Maybe a completely different concept, something we haven't even dreamt of yet, will emerge as the true description of quantum gravity and unification. That's just how science works. It evolves. But here's what I think is really important. Regardless of whether it's ultimately proven true or false in the experimental sense, string theory has already given us something incredibly valuable. It has fundamentally changed how we perceive the universe. It encourages us to look beyond the idea of just inert particles in empty space. It pushes us to imagine reality as something dynamic, vibrant, interconnected. As music, as vibrations, as these intricate patterns of energy weaving together everything we see and are. It offers a paradigm shift, focusing on harmony and resonance rather than just individual components. It inspires us to seek that deeper unity.
That's a really powerful point. It's less like thinking of the universe as this giant, cold machine, and more like it's a living song, a vast, ongoing performance unfolding across space-time.
Exactly. Think about the sheer wonder in that idea. You, me, the Earth, the Sun, distant galaxies, enigmatic black holes, the atoms in your hand, all potentially just different notes, different harmonies, played on the same fundamental cosmic instrument. Each vibration pattern is unique, creating the diversity we see, but it all stems from the same underlying reality, part of one grand symphony. An incredible sense of unity emerges from that perspective, and that, I think, is the real beauty and lasting value of string theory, whatever its ultimate scientific fate. Even if it never gets definitively proven, it provides this incredibly rich, poetic, and mathematically sophisticated lens through which we can feel the universe. It allows us not just to measure and calculate, but to stand in genuine awe, to sense the underlying music, to connect with the cosmos on a deeper, more resonant level. It fuels our wonder, and that's crucial for driving science forward.
That's wonderfully put, to wonder at it. This whole exploration really has been a journey, hasn't it? From thinking about tiny, indivisible particles to imagining this unseen orchestra of vibrating strings. It definitely sparks that curiosity and sense of awe, no matter what the final verdict on the theory turns out to be. It makes you think about what truth even means at these frontiers. So maybe, as we wrap up this deep dive, the most interesting question isn't the simple, is string theory true? Maybe it's more like, what does it mean for us, for our understanding of ourselves and our place, if the universe really is a kind of cosmic song? And if it is, what note are we playing in that immense, unfolding symphony?
Perhaps, ultimately, science and wonder aren't separate things at all. Perhaps they're just two essential harmonies playing together in the same eternal music of the cosmos, each helping us appreciate the whole incredible composition.
A beautiful thought to end on. Thank you so much for joining us today on this deep dive into the heart of matter and music. Keep asking those big questions, keep listening for those hidden harmonies, and never stop exploring the mysteries of our amazing universe. We'll see you next time.